In southern France, 35 nations have united to construct the most complex machine in human history. Budgeted at over $25 billion, ITER aims to replicate the power source of the sun here on Earth. Nuclear fusion promises virtually unlimited, zero-carbon energy, with zero risk of catastrophic meltdown.
Engineers must contain superheated hydrogen plasma, reaching 150 million degrees Celsius.
At 10 times hotter than the sun's core, no material on Earth can touch the plasma directly.
Manufacturing these components pushed global metallurgy, magnetics, and robotics into uncharted territory.
Massive subassemblies fabricated across Europe, Asia, and the Americas were shipped to France via custom heavy-haul transport.
Scientists from China, the European Union, India, Japan, Korea, Russia, and the United States share all technical patents.
The physics is simple. Fuse hydrogen isotopes together to release 4 million times more energy per gram than coal. Inside a 30-meter-deep seismic isolation pit sits the foundation of the world's largest magnetic confinement device.
400 seismic isolation pads protect the 23,000-ton reactor assembly against severe earthquakes.
Phase 1. Constructing the world's largest stainless steel vacuum vessel and magnetic cage. At 30 meters wide, the ITER cryostat is the largest stainless steel vacuum pressure vessel ever built. Laser welding seals the cryostat, creating an ultra-high vacuum environment to insulate the supercooled reactor core.
18 D-shaped toroidal field magnets form a magnetic cage to trap superheated plasma.
Each 17-meter-tall TF coil magnet weighs 310 tons, equivalent to a fully loaded Boeing 747.
Wound from thousands of niobium tin superconducting strands, these magnet coils carry 46,000 amperes of current.
At the heart of the machine stands the central solenoid, a 13-meter-tall pulsed superconducting magnet. Generating a magnetic field of 13 Tesla, the central solenoid is strong enough to lift an aircraft carrier. The world's largest cryoplant pumps liquid helium to chill 51 magnets down to -269 degrees. Vacuum-insulated transfer lines carry 12 tons of liquid helium throughout the magnet network without thermal loss.
9 double-walled stainless steel vacuum sectors are welded together to form a hermetically sealed 1,400 cubic meter chamber. Metrology teams verify sector alignment using sub-millimeter laser trackers across 44 distinct port openings.
Phase 2 complete. Now engineers install the plasma heating systems and heat shield armor.
When operational, superheated hydrogen gas transforms into plasma, levitating in a donut-shaped magnetic bottle.
440 individual beryllium blanket modules line the inner vessel wall to absorb high-energy neutron bombardment. High-pressure water circulating through internal copper channels removes megawatts of heat per square meter. At the bottom of the vessel sits the diverter, a 54-cassette tungsten assembly designed to exhaust helium ash.
Tungsten tiles in the diverter withstand thermal loads comparable to the surface of a spacecraft re-entering Earth's atmosphere. 3 neutral beam injectors shoot high-energy deuterium atoms into the plasma core, boosting temperatures past 100 million degrees. 24 gyrotron microwave generators beam 50 megahertz radio waves into the plasma, heating electrons like a microwave oven.
Combined heating systems pump 50 megawatts of heating power into the fuel, igniting fusion reactions. Heat exchangers transfer fusion energy from the vessel walls into secondary cooling loops capable of driving steam turbines.
Over 50 diagnostic systems monitor plasma density, temperature, magnetic turbulence, and impurity levels 50 times per second.
Resonant magnetic perturbation coils adjust the magnetic field in microseconds to suppress plasma turbulence.
Phase 3 complete. Now engineers deploy AI control systems and remote handling robotics. In the central control room, deep reinforcement learning neural networks predict plasma instabilities milliseconds before they occur. AI magnetic control loops adjust current to 36 magnetic coils 10,000 times per second, maintaining plasma equilibrium. Due to neutron activation inside the vacuum vessel, all maintenance is performed by heavy articulated robotic arms.
A 10-ton robotic manipulator enters port openings, unbolting and replacing damaged diverter cassettes automatically.
The tritium building processes fuel isotopes, recovering unburned deuterium and tritium from the vacuum exhaust. Breeding blankets containing lithium-6 absorb fusion neutrons, generating new tritium fuel directly inside the reactor.
Pneumatic pellet injectors fire frozen deuterium-tritium ice pellets deep into the plasma core at 1 kilometer per second.
Dedicated 400 kilovolt grid connections deliver pulse power, supplying up to 500 megawatts during plasma startup. Water-cooled thyristor converters transform high-voltage AC grid power into direct current for the superconducting magnets. ITER's target is Q10, inputting 50 megawatts of power to produce 500 megawatts of net fusion power.
Sustaining a 10-fold energy gain for over 400 seconds will shatter every previous physics record.
With ITER's systems fully integrated, a global race among private fusion startups has exploded worldwide.
Spurred by ITER's breakthroughs, over $6 billion in private capital has poured into commercial fusion ventures.
Korea's Kyostar tokamak set a world record, sustaining 100 million degree plasma for 40 seconds using high-density diverters. China's EAST artificial sun achieved over 1,000 seconds of continuous high-confinement plasma operation. Next-generation high-temperature superconductors allow private ventures to build compact, lower-cost fusion reactors. Projects like Spark aim to demonstrate net energy gain within smaller spherical tokamak designs before 2030.
ITER is experimental. Its successor, Demo, will supply 2,000 megawatts of electricity directly to commercial grids.
Commercial fusion power plants will generate steam to drive conventional grid-scale electric turbines continuously.
With deuterium from seawater and tritium bred inside reactors, fusion fuel supplies will last for millions of years. Fusion produces zero greenhouse gases and zero long-lived high-level radioactive waste, solving humanity's climate dilemma. 35 nations working together prove that global scientific cooperation can solve humanity's greatest existential challenges. A $25 billion masterpiece of physics and engineering that unlocks the energy of the stars for all mankind. These massive engineering marvels stand ready, proving that human ingenuity can ignite a new sun on Earth.